All right, we're going to jump into a new idea here, gravitational potential. This is very similar to electric potential. With electric potential, we were talking about the work done per unit charge to bring that small amount of charge, all right, in from infinity to that point in the gravitational field. So this is very similar to gravitational potential energy, except now we're talking per unit mass. Okay, that's what we're going to be talking about with gravity. Okay, so whereas with electricity it's per unit charge, with gravity it's per unit mass. Now gravitational potential is not very useful for us unless we're dealing with satellites here and such. But really, and we get more use out of electric potential dealing with voltage and circuits. That's what is able to move charge around and give it energy. But we are just going to focus on gravitational potential for a little bit. Do a few problems, okay, and then we'll put it in context a little bit more when we talk about satellites. Okay, so just get the definitions out here. Again, long, wordy, abstract. Sorry, just write it down. All right, work done per unit mass to bring a small point mass in from infinity to that point in the gravitational field. Symbol capital V, just like it was for electricity. It's easy to remember potential there with the V, right? And the formula, like we said, the change in electric potential has to be equal to the total work done per unit mass, or we sometimes also say change in gravitational potential energy per unit mass, all right? So this is the change, obviously. Potential at a point, just V on its own, right, is the gravitational potential energy, but at that point, which we can also define as, well, this gets rid of the little m, all right? So this is potential at a point. Okay. So at the base level, just as before, all right, our reference line here, okay, as with gravitational potential energy, the gravitational potential is equal to 0 at position infinity, okay? So V is negative for any finite separation. All right, bring it in from infinity, some point here, or, all right, we get that little guy right there. So what is the gravitational potential at the surface of the Earth? Well, we can just substitute in our variables here. All right, we get a value of negative 6.26 10 to the 7th joules per kilogram. All right, and over here, not to do 2 Earth radii, I'm just going to change the denominator, right, to 2 r and so it's useful, right, to be thinking of the change in gravitational potential energy as a change in gravitational potential times the mass, right? And in this case, the change in potential between these two positions was actually a positive 3.13 times 10 to the 7th joules per kilogram times that 1,500 kilograms. That means total energy. We have positive 4.70 times 10 to the 10 joules. Okay. All right, so derive an expression for the gravitational potential at the surface of a planet. Again, that's the same thing that we had before. We're okay with just calling it something like this and saying the surface of some random planet here. There we go. All right. So if we sketch a graph of a gravitational potential of a planet versus the distance from the center of the planet, it looks just like before as it did with the gravitational potential energy, V, R. Right, so V is the y-axis there, sorry. And again, R of the Earth versus the planet. Looks like that. So here we got a graph that shows variation of gravitational potential due to the Earth. With distance r from the center of the Earth. The radius of the Earth is 6.4 times 10 to the 6 meters. All right, so if you actually look here on the graph, it looks like it comes pretty much to that point, and that gives us that value of gravitational potential, all right, at that point, which we calculated in the previous problem. So here it asks for the gravitational potential, determine the energy to put, a satellite of that mass into an orbit that high above the Earth. So what we're going to find is 3.6 times 10 to the 7. Notice here the axis is 10 to the 6, so it's 36 is what we're looking for right here, all right? And what we want to do is just get this point over here, all right? When we do that, all right, we're going to be taking these 2 points, we want to find the difference between them. So delta V, all right, to be equal to negative 1.15 times 10 to the 7 joules per kilogram, all right, minus negative 6.26 times 10 to the 7 joules per kilogram, right, and that's going to give us a positive, is equal to a positive 5.11 times 10 to the 7th joules per kilogram of the units there, okay? Given that the mass is 10,000 kilograms, all right, delta U is equal to delta V times M, which is going to give us 5.11 times 10 to the 11 joules, and actually I'll show it as well, so you should see it. So positive 5.11 times 10 to the 7 joules per kilogram, all right, times 1.0 times 10 to the 4 kilograms. All right, and we got 5.11 times 10 to the 11 joules. All right, so that's an example problem there. All right, so what is the net gravitational potential of a spot midway between the Earth and the Sun? So when we deal with gravitational potential, it's just like the electric potential, all right, where we're going to add it. Now with electric potential, we have attractive forces and we have repulsive forces, okay? So we may be adding or subtracting the potential, but here it's always just going to be added, all right? And so for that reason, when you find out the gravitational potential due to the Sun, halfway between the Earth and the Sun, you get a value like this. I suggest you check my numbers. Actually, plug it in. I'm not going to do all the work right now. This is going to be a long enough video as it is. All right. And here for the Earth, we get this value for that position. Okay. And when we add the two of these together, well, we see that the potential doesn't change very much because the potential is dominated by that of the Sun. All right. So if there's a spot between the Earth and the Sun, is there a spot between the Earth and the Sun where the net gravitational potential is 0? If so, where? If not, why not? No! Right? Both are negative. You always must do some amount of work per unit mass, bringing your mass in from infinity. Okay? And with two objects doing the attracting there, you have to work against both of them. All right? So the amount of energy that you have to remove from the system is going to add. All right? We're doing that work. So no, why not? Because Chorman said no. Okay? You must always do work per mass. That's the potential part. Okay? And with two objects, that adds, if you will. Okay? That's combine the works. Yes, it works. Okay, sketch a graph of the variation of net gravitational field as a function of distance between the Sun and the Earth. I believe it would look something like the following. So this is where the Sun is, this is where the Earth is, okay? This is potential, and yoink, something like that. All right, it'll take a while before we get down. Okay, so let's compare all these values. All right. always difference in new variables is what I meant to say. So for gravitational field, this is actually vector G, right, as such. That's equal to big G, big N, over squared. Gravitational force, S of G, over squared. Okay. Both are vectors. Vector. We can do the same thing actually when it comes down to electric fields. We got all these nice little patterns, it appears, with the formulas of units and these quantities. So, yeah, it's interesting how these forces work out like that. So over here, these are both scalars. All right, U here, G, M, little m over R. All right, also a scalar. And here, the unit is joules per kilogram. Here, the unit is joules. All right, and that's it. Those are the comparisons. All very similar units. Excuse me. Yeah, styles units.